So our first exercise. For this we will use the H7S, we will use the Octo SPI memory, and we will create basically 3 applications. One application which will be the toggling of the LED, which will be stored inside the external memory. Then we create the second application, which will be called the bootloader, and the job of this application will be to initialize the external memory and jump into this external memory. And the last part will be external loader, which is not directly used all the time on our microcontroller, but it's mainly for our Cube IDE or Cube programmer to teach him how to download the data on the external memory. About the external memory loader, if you're using the internal memory inside the STM32, we already know this memory, or all the manufacturers know his device and his memory, so we already prepared this project. But for the external memory, what is unknown is which pins will be used, which peripheral will be used, what will be the microcontroller speed, if it's needed to enable the powers for all the LDOs and so on. So for this, for every unique board and every unique memory, for this combination, it's necessary to create external loader. And this will be used only during the programming when you want to download the code into the external memory. It will be automatically used by the tools, by the Cube IDE, IR, Kyle or Cube programmer. And he will take this project, this external memory loader, put it into RAM and use the functions from this project. So it's not normal application, it don't have main. It's mainly have the functions which were defined by the Cube, by the programs which will be using this loader, which needs to be there, and he will call them specifically during the programming. So we can start by opening the CubeMX. We will start from the new project. So click File and the new project. It may download the last test database to be sure that we have all the devices. So in this, we will start with the completely empty project, so no board, no example, and we type H7S3 and the one which is on the Nucleo, but we will start with the empty device, so double click. We want to use the default MPU configuration, which I will explain to you what this means and why to use it. So click on yes. The CubeMX asks us why we want to create the default memory protection unit configuration, and why? Because the Cortex-M7 is quite complicated processor, using some advanced techniques to increase the performance, and one of those techniques is the speculative read, when the processor basically can randomly fetch data from the memory. But this unfortunately decreases the performance of this memory. So for this reason, we will protect the memory against this speculative reads on the locations which we know that there is no memory. So for this reason, we're using this MPU unit, and we tell him that we will define one region, usually the region 0, which is the lowest region which exists. Then for this area, we want you to not access or do the speculative reads. So far, we disabled this for all the external memories, and during our exercise, we allow it only for the SPI. This configuration we require for all the M7 Cortex devices, not only for the H7S, but for all of them. So it's basically the default configuration. Don't forget on that, please. It will save you a lot of the issues later. Okay, we are now inside our project. What I want now to mention that there is the new thing that now inside the peripheries we can see the 3 columns. The one column will be for the bootloader. What we check here will be added into the project for the bootloader. One which we check with the app will be added into the application, and third one will be added into the external memory. What this means for us, that everything which is marked inside the bootloader, which is here, will be basically stored inside the STM32H7 memory, so inside this 64K flash. Everything which will be marked as an application will be then stored into the external memory, and everything which is marked as an external loader will be then used by the Q programmer or the Cube IDE to be temporarily stored into the RAM and used during the programming of the device. We can start then with the MPU configuration first, because we already started with it. So we will go here into the Cortex-M7 boot. Here you should see that we have already this default region, which is already defined. This was the region which I was talking before. And now we will define the new region. The new region will add here the support for the SPI area, which allow us to access this external memory area without any issues. In case that you don't want to use any external memory, you don't need to define this region. This external memory area, the address of this area, depends on the peripheral which we are using, because we will use the external SPI1. I will put here the 90 million. It's the 9 and the 7 zeros. The size of the region should be the size of the memory, which should be 32 megabyte. All the region will be used. And here all these parameters can allow me to access the memory. So I want the access at least for the read. And I want to execute the instruction, so this will be enabled. I don't want to share this memory with any other peripherals, and I want to make it cacheable and bufferable. So it means that I can use the caches with this memory. And this is the second step which I wanted to here, to enable the data cache and the instruction cache, which will increase the performance of the external memory significantly. Now I can go into the MPU configuration also for the application, but because I already set it inside my bootloader, I don't want to set this inside my application, so I will disable this option here, but I still want to enable the caches. And this is our MPU configuration. This you should do on the all M7 cores, not only this one, so this operation is basically default for the all Cortex-H devices or the F7 devices. Now the memory. We will use the memory which is on the Nucleo board. I have here the part of the datasheet of this memory. It's the flash memory. The size is 256 megabits, which is 32 megabytes. It's running always on the 1.8 volt. And it supports the normal SPI mode and also the Octo SPI mode. And also this memory supports the DTR, which is the double data rate. So it will send data on the rising and the falling edge. And another important parameter is the maximum speed. In the single data, in the SPI mode, it's 133 MHz. On the Octo SPI, it will be 200 MHz. This is information which will be used during the configuration, so this is why I wanted to show them to you. Another important part is how the memory is connected to the STM32. The memory is basically connected by the 8 pins and the clocks and the chip select, of course, and also the data strobe signal. And the important part here to mention that the memory really running on the 1.8 volt. And on the STM32 part is connected to the port belonging to the Octo SPI peripheral, and this port is also powered from the 1.8 volt, but the rest of the STM32 is connected from the 3.3. So for this dedicated pins, I can have the separated voltage domain which running on the different voltage than the rest of the microcontroller. I was talking about the speed of the OSPI, but also it's good to mention the speed of the STM32. So I have here the datasheet pictures from the STM32 datasheet, when we can check the maximum speed of the STM32 OSPI peripheral in the different modes. What is important for you, for us, we will run it most probably in the DTR mode, and we will run it on the 1.8 volt. So far there is the maximum speed on the 190 megahertz, but for the complete range, and it will be added in the next revision of the reference the datasheet, then the maximum speed on the 1.8 is 200 megahertz. So we can run the memory on the maximum speed. What is the second important thing is the speed of the pins, because not only the periphery but also the pins need to be same fast. And we can see if we have the normal configuration, the maximum speed is only 80 megahertz on the 1.8 volt, which is not so good for us. But to solve this issue, we have the feature which is called high speed low voltage, and if we enable it on the 1.8 volt, we can run up to 200 megahertz. So if we are running the normally, if we have the normal 3.3 volt, it's okay. But in case that we have the 1.8 volt, the speed is then limited of the pins. But there is the workaround for it, which is called the high speed low voltage, which we can enable and allow the pins to also run to this maximum speed. But it have one important drawback. If you accidentally enable this feature and you're running these pins on the 3.3 volt, you may damage them. So you need to only enable it if your voltage is lower than the 1.7 volt on this dedicated pins. And because of this problematic complication, you need to enable it on the two places to be sure that you not enable it by accident. One of these places is the option bytes, and the second one is the peripheral called SBS. So we can now try to enable them. First, we can do it inside the CubeMX. So simply here search for the SBS peripheral. We will enable it for the bootloader and also for the external loader, because on the both we want to run on the maximum speed. Here we simply activate the peripheral, and here we will select which port of the microcontroller we want, and this dedicated pins are on the port 2. So we enable here the port 2. We need also to modify this option byte for the high speed low voltage feature, and best way how to do it is to use the Cube Programmer. So we can use the open the Cube Programmer tool. Simply here we click on the connect. First we need of course to power the board, so put the USB-C into the debug connector of the STM32 Nucleo board. You click the connect. He will show you the device and the board which we have, so it's the main board which I wanted, and the option bytes are here inside this third tab, and we want here to go down into this user configuration 1, and what we are searching here is the XSPI2 underscore high speed low voltage feature for the port 2. So we check it here and click apply. So he should program the device and tell us that the device is successfully programmed. You can read it back to see that it's there, and it will stay there forever until we change it or reprogram it from the code itself. So this was the SBS. The last general thing which I wanted to configure here is here inside the RCC. And we want to change the power supply, because on the Nucleo board we're not using the SMPS, but we're using the LDO power supply. So switch here the SMPS to the LDO. And this is the basic general configuration for the board. And now we can finally move to our external memory. And we will talk here about this XSPI1 and the XSPI2, and I will try to explain you why to use which one. So I decided that I will use the XSPI one. Basically, the both of them are equal, so you can use any of them. But for this example, I use the XSPI one. The difference between them is mainly the area of the code when the memory map feature is used. And for the XSPI one, it's the 90 million. For the XSPI 2 is the 70 million. And I want to use it inside the bootloader because the bootloader needs to enable the external memory, and also inside the external loader. Inside my application, I don't want to use it because I will already run from the external memory, so it will be already configured, so don't need to do it from the application. And first I need to select the mode. I can use the different mode from the single, dual, quad, octo to the hexa in case that it's supported on the package or the hyperbus memories. In our case, it will be the octo SPI. The second part is the port. We have the two options, the port 1 or the port 2. What this means? It is very simple. Usually the both of these octo SPI peripherals are connected all into the two ports, and you can choose if the octo SPI peripheral will use the port 1 or the port 2. They have the separated pins, and the both can use the octo SPI 2 can use the port 1 or the port 2, it depends on you, or you can even multiplex them on the same port. So you will save this 8 pins, for example, and the both will use the port 1, but both will have the separated chip selects. In our case, the octo SPI which we are using is connected to the port 2. So we will select port 2 octo SPI, and the same for the chip select. We using the chip select from the port 2, but it's the chip select number 1. So you should have here inside the pinout the letter small I. Now I would like to explain to you the parameters configuration, that you understand what you need to configure, what you don't need to configure. And we will start from the top and go to the bottom. But I think it's very important to understand in case that you have the completely different memory, but you should configure there and but not. The FIFO threshold we can keep at 1 because it's used mainly if you're using the octo SPI as a SPI and you loading the data there manually by the DMA or the core, but we will use it in the memory map mode, so it will be visible as a part of the microcontroller memory. So this will be then handled by the peripheral itself, so we don't need to pay attention to this mode. The memory mode, it will be enabled automatically, so we are not forced to enable the memory mode by ourselves. But what we need to do is to select the type. Don't be scared about the name of the vendors in case that you have the different vendor which is not here. It's not like it's tied to the vendor type, but mainly how the memory is accessed. For this I have the one slide. The main can be in the DTR, which unfortunately every vendor created a little bit own approach how to address the memories and how to handle some signals. You can see that, for example, the micron inside the DTR addressing the sending data, first data 1 and the data 0 and the data 1, and the DQS signal is inverted. On the other side, the macronics sending the data in the opposite way, then the first data 1 and then data 0. And DQS, it's not inverted. So I recommend to check inside the reference manual and see which configuration is there. In case that you have directly the macronics memory, there is nothing there. They keeping their own standard, so they will have this approach. And we have the macronics, so we select the macronics. Also, we know the memory size because it's 256 megabits. Be careful, here it is in the bits, so 256. The another parameter is the chip select high time. This is the time how long the chip select is high. This value depends on the memory And in our case, if we look into the datasheet from the memory, we see that the read to read time needs to be at least 10 nanoseconds. In case that we have 200 megahertz, then one clock cycle is 5 nanoseconds. We need to put at least 2. You don't need to pay attention to the write RSM program because this will be handled by our software, and we are much slower than this 40 nanoseconds. So I think the 10 nanoseconds for the maximum efficiency is the limit for us. So we will here put 2. Don't forget to mark it. Be sure that it's there. For the other parameters, we have the free running clock, which means if the clocks are stopped during the chip select high, which will decrease also the consumption of the whole system, or the clocks need to run all the time. It depends on the memory. Our memory supports the stopping clocks during the chip select high, so we will keep it disabled. The second option is the clock mode. If we have the clock during the chip select, where it's chip select high, if the clock are in the high state or they are in the low state. This is the standard SPI configuration. It's also described as the mode 0 and the mode 3. We will use the default value, which is low. So the clock, when the chip select is high, the clock are low. The parameter wrap size is used in case that the memory is supporting the special wrap commands, but in our case the memory is not supporting it, so in our case we keeping the default value not used. The parameter capacitor is that we can divide the clocks which are going into the Octo SPI periphery, and we can divide it. In our case, I will plan to use the 200 MHz as a clock source for the Octo SPI, so I will keep here no division, but also if we using the memory manager library, it will handle this configuration, so we don't need to change it at all. The sample shifting, it's mainly used if you don't using the dual data rate mode, and in the normal way you will, for example, sample on the rising edge of the clock. But in case that you have the big capacity on the line, or you are running on the edge of the maximum frequency, like the 133 MHz, you can delay this sampling by the half of the clock cycle. So you have more time to reach the level which you want, and usually it increases the number of the compatible memories which can be used. In our case, we will use the DTR, so we cannot use this option, so we will keep it disabled. But for the delay hold quarter cycle, also can be used with the dual data rate, and it will not sample on the falling edge, but in the middle between the edges, which will again increase the potential to use these memories. Unfortunately, on the H7R, this option is not there anymore, but on the older memories, if you have it, definitely use it in case using the double data rate feature. And the chip select boundary, it's mainly how long can be the chip select be down in case we're not using it, so it's not issue for us, so we keep it disabled. The maximum transfer in case that we multiplex two memories together, which we are not doing, so we don't need to limit the maximum transfer time. For us it can be also the infinity. And the refresh rate is in case that we have, for example, pseudostatic RAM, which needs to rise the chip select after some time to be sure that it can refresh the internal memory, but we have the flash, so for us also no problem. And again, the chip select, we have the chip select 1, which should be there by default, so we don't need to change this parameter. So only what I need to change in my case is then to put here the delay hold quarter cycle, to be sure that I will not forget on it, but on this device it have no meaning, but it's good to be sure that we cannot forget on this. And I think we have here no other configuration. Here in the MMT we can select that we are the flash. And this is all from the XSPI configuration. Now we can finally move to this external memory manager, and I will explain what it is doing. We will use this library for the bootloader, basically to help us with the configuration and also for the external loader. So check the bootloader here, and also activate the library. I want definitely from him to generate me the code, and I have the more possibilities. I can select the execute in place or the load and run. In our case, we will select the execute in place. What is the execute in place? It's very simple. If we have the code in the flash, what he will do, he will simply, after the reset, use the code inside the internal flash, configure the external memory, map it as a internal space of the STM32H7, and then he simply jumps into the external memory. So your code will be physically executed from this external memory. So this is this execute in place option. The second option, load and run, means that after reset, he will configure the OSPI in the read mode and simply load the data from the external memory and put it into internal memory of the STM32. Why you use this option is mainly in case that you have the external memory which is not possible to directly map on the STM32. For example, it can be the SD card, for example, or the eMMC card, which cannot be internally mapped. For the external flash, it can be theoretically used in case that you want even more performance, because the internal RAM is much faster than the external flash ever will be, because it's inside the STM32. So in our case, we're keeping the execute in place. Here it's nothing else which we can select, and we can check inside the memory 1 and the driver which we want to use. In our case, we will use the external NOR memory, and if we will use the SFDP protocol. About this I will talk a little bit in the few moments. And we want to use the maximum number of the data lines because we have 8 lines, so we want to use them all to even increase the performance of this external memory. So now, what is the SFDP? The SFDP is basically the reason why we use this external memory manager. And it's when the multiple vendors of the memories, the issue is that each memory is a little bit different. So it was standardized that on each memory will be the register which contains information about this memory. This register, it's called the SFDP, and it was also standardized by the EDX standard. And what the external memory manager will do, he will access the SFDP register, he reads it, he parses the content of this register and configure the external SPI that way which is aligned with this SFDP configuration. So he basically configured for you all the memory operations, so you don't need to read the datasheet, check which command, how to configure it on the STM32. He can do it for you. But of course, the prerequisite is that this memory has the SFDP protocol. Then usually they announce it inside their datasheet. In case that you don't have the memory with this protocol, you need to create this driver by yourself, which is more complicated, which I will show you inside the exercise number 2. And now we can return to the last part, which is the external loader, which we need to configure too. External loader is available only for the external loader project. We can activate it, and there are some informations which we need to fill for him because he cannot read them for the memory, because this information are used before you start using the board itself. It's mainly for the Q programmer to know how to program the external memory. So the memory, we have only memory number 1, so there is nothing. We want to generate this for the toolchain which we are using, so you can keep it here, the default option. Otherwise, we can create it only for the programmer, or if you have the IR, he will generate it for the IR or the Kyle. It's up to you. The name, it's how we will recognize our loader, so I can name it somehow 7 for example, you can see that he already prefilled the area when to expect the external memory. And we need to fill a few parameters like the number of the sectors and the sector size, which is very important. So, number of the sectors, for this you need to open the datasheet from the memory, and I will tell you that this memory is 8192 sectors, and the one sector for the async is 4096 byte. For the page programming time, I am okay with the default values which are here in case that you want to increase the performance, cross-check these values with the datasheet from your memory. The higher time, it's not a problem. The shorter time can be the problem because you will have no time before the next restart. I forget the page size. Page size is here the 256 bytes. Which is 100 hexa, so the default value, it's okay. So this is all from the configuration, and we can move to the clocks. We can set here the maximum clocks. We don't need to select any different clock source, so I will select here to PLL to make it faster. I put here 600, tell OK. He should search for me the valid combination of the clocks and the settings for the PLL. Which I hope he will do just now. Yes, now he only tuned the dividers to fit. So I have the 600 megahertz for my core, but I also want to set the speed for the OSPI, and I want to set it for the maximum frequency, which will be the 200, because if I use the 300, he cannot run the memory on the 300, and if we divide it by 2, it will be 150, so I will run slower than I can. So I will want to set it to the 200, so I will use this PLS, for example, and I will set the PL by myself. I have the nodes what to set there. Then it should be 50 here. In the multiplier, in the divider it will be 450, and I think here will be 4, which give me the 200 megahertz, so which ensure that the mine OSPI will run on the maximum possible speed, which is limit of the H7 and also limit of the memory inside the DTR mode. So the last operation which we want to do inside the CubeMX is go to the project manager, select the location where you want to have your project, and I will create the name of the project. Exercise 1, for example. Don't forget that we want to create the bootloader project, application project, and also external loader project, because so far we have no external loader. In case that you already created some external loader for this board, you don't need to create the external project and sometimes the bootloader every time. After this, you can only create the application, because the bootloader can be generic, and also the external loader for this nucleo will be always fixed. So then afterwards you will only create the application project. But I want to change the toolchain, so I will create it for the Cube IDE, and this all from this configuration, and I can click on the generate the code. My code is generated, so we can click on the open the project, and we should have the Cube IDE opened. It's just importing my project I created for this empty workspace, and we can close this info tab after he finished the importing. Okay, he's still importing the project. Okay, and I should have here my exercise 1. And you should see that I have here 3 projects. So I have the application, the bootloader, and the external loader. First, I will probably add the LED toggling into my application. So I will open the application. I will go to the source, core source, and inside the main. And I will add the simple LED toggle. And this is one thing which I forget. I forget to initialize my LED, but no problem. We will do it just now. I will put here the HL GPIO, I can press Ctrl space to whisper to me, and I want to toggle pin, and I think it will be GPIO D and GPIO pin underscore. Sorry, I didn't delete this. GPIO pin underscore, I think it will be 13, and we can mark it here, and here we pull the HL underscore delay and put here something like the 500 milliseconds for the delay. So this project will only stay here and toggle with the LED and then wait 500 milliseconds. But what I forget is to initialize the pin 13 inside my CubeMX, so I need to return to it. To enable this pin PD13, I need to return back to my CubeMX, which I forget. I will click on the pinout, and here I need to search for the PD13 on the BGA. Is not simply job. He will highlight it for me, so I will select here this pin as output, but be careful, it's not enough on the H7R. You need to right click on this pin and click on the pin reservation, and we want to use this pin inside the application. So we will select this, and we can regenerate our project, and it will be refreshed inside the Cube IDE. The project is regenerated. You can see that now I have here the GPIO in it. The last operation which I wanted to do, it's inside the bootloader. So we will go to the bootloader, core, source, and inside the main.c. You can see that he will initialize the device how we want. He initializes the clocks, he initializes the SBS, the external memory, and also we use the external memory manager. And then he will call the boot the application, which means that he simply jump into the application. He enabled the memory map mode and jumps into the application. But there is also one thing which I want to do, and it's to enable the invalidate the caches. So I will add here the code to invalidate the data and invalidate the instruction cache. So otherwise I don't need to change anything inside the bootloader. In case that you will create your final application, maybe you will want to cross-check the validity of the external image or something like that. For us this is enough, and we can compile all of them. You need to compile separately the bootloader. We can compile the application, and then also the external loader. My projects are now compiled, so application, boot, and also the external loader. When the external loader finish compiling, there is the script which is executed, and the script is searching for the Cube programmer and also for the Cube IDE. In case that he will find them, he will try to copy the external loader into these folders. In case that you have, for example, the Windows restriction and your Cube programmer or the Cube IDE are in the program files, it may not succeed. In this case, you need to do it manually, or you install the Cube programmer somewhere else. And how to do it? You simply open any browser. You look into the memory manager, into the debug, and here will be the executable, the ELF file. And you locate for example, the Cube programmer. You locate here the binary, and here should be the external loader. So these are all the externals loader which exist here, and only what you need to do is to take this, rename it to the STLDR, only change the end of the name, and copy it inside the external loader. This is all of what the script is doing. So your project is basically the external loader. There is nothing hidden behind. Our projects are compiled. So how you can load them into your device? You can do it separately to first load the bootloader and then the application, but this is quite annoying. You can do it on one download, so we will select the application. I will click the debug, and he should open me the debug configuration. Inside the debugger, there should already be selected the external loader, which I just created, so it have the same names, so he already knew it, and he probably downloaded it into the Cube IDE and also into the Cube programmer, so I will be able to flash the external memory. But what is important for me, here inside the startup, I have this application executable, which will be downloaded and also run for the debug. And I can add the second executable, or more than the one, and I will select the bootloader, the active one. I want to download it also, and I will add it. On the here, be careful, he's starting from the executable with the arrow here, and I want him to start with the bootloader because I want the bootloader to be first. So I can select it here and move it to up. So now the bootloader will be executed first. And I can click on the OK, and he should start flashing the STM32 internal memory. And also he will start the flashing the external memory too. And he asking to change my perspective, so it seems my configuration was okay. So now you can see, if we look into the program counter, that we are on the address 8 million, which is the internal flash. So this is my bootloader, and I can run it. On the STM32 Nucleo, you can see that the orange LED will blink. And if I pause it, I should be somewhere probably in the get tick. I can here check where was it was the delay function, and I was somewhere in main. And if you look on the program counter, I am on the 90 million. So this code is executed from the external memory. So what we did, that we downloaded the bootloader in the application same time, and we can also debug them in the same time. So I think now it is working, so we can close the debug. It can happen that also you have the issue with the external loader and you would like to debug it too. You cannot directly debug it when he is flashing your application, but at least there is the template which allow you to debug the external loader as a normal application, as a simulation of the downloading. I only want to explain how this is done and what the external loader should have. Usually the external loader have defined API, the functions which the Cube IDE, Cube programmer or the IR or Kyle require to be there. It's usually the init, write function, mass erase function, erase sector erase function, and the verify function. And optionally, in case that the memory is not possible to map on the internal space of the STM32, they can be read. In our case, there is no read. And how it is done, he usually called the init. He must call the init, so there is usually the reset of the memory, the rationalization of the memory, and then he called one of this function. There is the write, mass array, sector arrays, verify, read, and then again he goes to the init, and then he again can choose different function. So in case that we want to debug it, we can. We will select here the external memory loader. We will run the debug. And there is created the temporary main, which is not normally used inside the loader. It's used mainly for the debugging. And we end up inside this main, which have the same state with the functions which I just presented to you. So you see there is the init function, write, mass arrays, sector arrays. And you can step over it. He should by default call the init. In any step he will call the init, and then he will go into the wait state. And in case that you want to check any of those functions, you can best is to add the switch variable into the watch. And you can change the value of the state. So for example, I can select the mass array state and I can check what is this will be 0, 1, 2, 3, 4. So it will be the state number 4. I should try it by chance because he will show me what it is. And it will, when I press, move me into the mass arrays, and I can step up or step through the function how I want and see what the device is doing. This is in case that you want to try the operation one by one, that you will try the init, you will try the write, you will try the read. I can run it, and he should again return back into the default state. In case that he didn't stop somewhere. So this is for the debugging. The debugging of the external memory manager is not so pleasant because of the complexity of the parsing. But in case that we will try the exercise number 2, when we will be creating the external loader, it can be quite useful to see what is happening there and to simulate all the steps. To conclude, we finish our exercise. So what we did, we learned how to configure the XSPI peripheral. I'll show you how to configure the memory manager, which basically did everything for us. So there was nothing to do or write on our side. So we didn't need to touch the bootloader or the external loader at all. We mainly created the application, and this is because the SFDP protocol inside the OSPI memory. I also showed you how to debug the application with the bootloader, so it will behave as a normal project for you, and also that it's possible to debug or simulate the debug of the external loader. Now, when you already created the bootloader and the external loader, in case that you want to create the more different applications, you don't need now create the bootloader and the external loader again. You can use the ones which we already created, and you will only create new applications. So it will offload us. This is only one-time thing for specific device and the specific board and the memory. So in case that you change the device or the pinout on the board or the type of the memory, you need to create new bootloader and the new external loader for this combination. So this all from the hands-on, and we will move to the hands-on exercise number 2.